Hello and welcome to another EE140 video. Today's topic is electromagnetic induction, particularly Faraday's and Lenz's law. We'll be discussing how these two laws work in conjunction with each other. So without further delay, let's go ahead and take a look at our example. In this example, we are given a thin copper wire, radius r, placed in a magnetic field B that is given by this function. Okay, so we could pause here and just analyze this information we're given. So we know that it's going into the negative x direction because of that, but we are given a zy axis. So what I usually do to determine the axis, I just write down y, and I always designate that as my pointing finger. You could also have your own way of finding out the axis, but you have to be consistent with them. So my z is my middle finger, x is my thumb. Right, and from here we could just draw out this one. So we'll copy this one, we'll copy this axis, but just kind of rotate it a little bit. Right, remember they're all orthogonal with each other. Since z is given on top and y to the right, so we have middle finger pointing up, pointing finger pointing this way, and our thumb is pointing this way, which makes this x-axis. So I could write here that x, or positive x, is going out of the page, therefore our negative x is going into the page. Let's also take note that b is given with sine function. So sine is a increasing function because, sorry about that, starts at 0, goes up, goes down, comes back up. So sine is an increasing function. As opposed to cosine, where the wave starts at 1, goes down, goes up. So cosine is a decreasing function. Okay, so for now let's just take note that b is going into the page and increasing. Let's write it down over here. And it's uniformly spaced, so it's anywhere in the plane. So next we're given a radius increasing at a rate of 50 centimeters per second, and that is starting from r is equals to 0 when t is 0. It's asking us what is the direction and magnitude of the induced current on the ring when radius is at 1 meter. So when r is equals to 1 meter, we don't know what the time is yet, but we need the I induced, direction, and magnitude. Okay, so let's process that real quick. So r starts at 0 and goes to 1. Okay, so that's 1 meter, and we are given a rate of 50 centimeters, but we're dealing with meters here, so let's convert that. 0.5 meters per second. Just the meters cancel, so we're left with 2 seconds. 1 divided by 0.5 is 2 seconds. So when r is equals to 1, t is equals 1 meter, t is equals to 2 seconds. We have a changing radius. Okay, let's write down r increasing. Okay, so what else do we need to analyze? So we have 1 meter resistivity. Okay, let's take note of that as well. But pretty much we're ready to find the I induced, and we get started by finding the flux or magnetic flux. There we go. And magnetic flux is pretty much magnetic field flowing or passing through this closed loop, right? The circle of thin copper wire over here. And that is given by integral v dot dA, which is the same as v dot a cosine theta, theta being the angle between magnetic field and the surface of the area. And since surface of the area is facing us or into the page as well, and it's completely parallel with the B field, that just becomes BA, because cosine of 0, which is 0, the angle between B field and the surface area, is 1. So cosine 0 is just 1. So we have BA. But that only works here if, you know, the field, magnetic field, is parallel to the area. That just becomes negative 10 sine 0.5 t times the area of the circle is just pi r squared. Okay, we could separate the constants with the variables. We have 10 pi times r squared sine 0.5 t. Okay, now that we have flux, we could find out V EMF, or the electromotive force, and that is given by negative d flux over dt. And this is pretty much the essence of Faraday's law. Okay, so this over here is change, and we have a negative here, right? So what Faraday's law is pretty much telling us is that induced EMF is opposed to the change. So if this is change and this is opposed because it's negative, opposed, and that is VMF, oppose the change in flux. Okay, so we just negative times negative 10 pi, so we just have 10 pi, and then this one we have to perform product rule. So quick reminder, product rule is if we have two functions and then we need to get the derivative, we just do f prime of g plus g prime of f. Okay, let's put that in the sign. So let's designate r squared as rf and the sine function as g. derivative of r squared is just 2r dr dt, and then just the sign, 0.5 t, okay, plus, okay, we're gonna go down a little bit here, plus derivative of g, which is need to perform chain rule as well, so it's 0.5, and then f, that's r squared, and then cosine 0.5 t. Okay, let's just rewrite that here. So that's 10 pi 2r dr dt sine 0.5 t plus 0.5 r squared cosine 0.5 t. Okay, let's just put that in the box so it's clear. So now we can scroll down here, get some more space. So now that we have our VEMF, we could find I induce, and we could obtain that by dividing VEMF by R. So this is just like our Ohm's law. V equals IR, and to find I, we just need to divide V over R. So what is R? So we have a resistivity of wire that is 0.2 centimeters, or 0.2 ohms per centimeters. So it's 0.2 ohms per centimeters. So what that's telling us is 0.2 ohms per length. But what length? So it's got to be the length of this circle, and the length of this circle is just its circumference, which is 2 pi r, right? But we know that r, when we're looking for I induced, is at 1 meter. So we just multiply this by 2 pi 100 centimeters. Okay, so we just converted 1 meter back to centimeters. Now centimeters cancel because this one is underneath. Okay, so now we're just left with 0.2 ohms times 2 pi 100. 0.2 times 100 is 20, times 2 is 40. Let me just get my calculator real quick to get, so that is 0.2 times 100 times 2 pi, and we get a value of R is equals to 125.664 ohms. So now we're ready to calculate for I induced. So we'll just write down the top, which is VEMF, and since we already have the values for R and T, we substitute that as well. So that's 10 pi 2 times 1, remember 1 meter, and dr dt is just the change, rate of change. So dr, so r went from 0 to 1, so that's 1. dt, t went from 0 to 2, so it's just 1/2. Sine 0.5 times, what's t? It's 2 seconds, plus 0.5, 1 squared, is 1 meters, cosine 0.5 times 2, because of time, right? All over 125.664. Okay, all right, so the value I got for top is 34.8 9226. That's divided by 125.664. 34 divided by 125.664. And the value I got is 0.277905. And remember, that's current, so that's amps, or I could just say 277 point, let's keep it at 9, milliamps. So there we have the magnitude for our I induced. So magnitude I induced. Okay, let's box that. And I wish we could say that we're done, but we still need to find the direction of this induced current. So to determine the direction of I induced, we need to understand what Faraday's and Lenz's law is trying to tell us. Okay, so Faraday's law tells us that induced EMF is to oppose the flux, hence the minus sign over in this equation over here, right? And that is supported by Lenz's law, which states to keep the magnetic flux unchanged, the system induces a B field, which is B induced, and that cancels out the increase in flux. So let's take a pause and think of that, or maybe we should illustrate that. So if this is the system, we have thin copper wire ring, okay, and B field is going into the page, okay. So we have two things that's increasing. We have B field increasing, and then we also have R increasing, okay. So we could all agree that flux going into the page is increasing. And Lenz's law is stating that to counter that, or to oppose that, the system induces a B field. So for example, we have three here, we have three, let's say we have three arrows in our system right now. If you put another one, what Lenz's law is telling us is that the system will counter that by putting the B field, B induced, that is opposing the change. So if we put another one here, there's going to be another B field, B induced coming out to oppose that change. Okay, so with B induced, alright, coming out of the page, and we designate B induced as our thumb, right thumb, alright, we could determine the direction of I induced as the curl of our fingers. Okay, so with that B field, or our thumb, pointing out of the page, our I induced is going to be going counterclockwise, right? Okay, so there we go. So just to summarize everything that we have, right? So it's asking R1. So when R is equals to 1 meter at T equals 2 seconds, right? The system or flux is increasing due or because to B increasing and R increasing. And the system, to counter the change in flux, the system induces a V field, V induce. Which in turn generates I induce, in turn generates I induced. And I induced is equals to the magnitude 277.9 milliamps, and it's going counterclockwise. There we have it. Okay, I hope this video is clear enough for you. If not, go ahead and ask our TA or ask the professor. Again, thank you for watching and have a great day.